So X-ray crystallography is how the structures of these crystalline solids are determined. And as you can imagine, it involves a lot of experimentation and a lot of trying different angles and measurements and geometry and stuff like that. We're just going to look at the answers now. What are the different types of crystalline structures? When we refer to a crystalline lattice, we mean the regular arrangement of atoms within a crystalline solid. And the way that the atoms or ions arrange themselves is determined by energy. The particles are going to arrange themselves in a way that minimizes their energy. And so depending on the relative sizes and charges of those particles, they will arrange themselves in different ways. We describe these as by looking at unit cells. A unit cell is the smallest divisible unit of a crystal that, when you repeat it in 3 dimensions, reproduces the entire crystal lattice. So in this arrangement, the unit cell is shown here. If I take this pink triangle, that's not a triangle, that's a square. I just failed kindergarten geometry. If we take this square and repeat it over and over and over again, we will get the arrangement, and that's what we're looking for. In this diagram, the circles represent lattice points. The lattice points are where there's an atom, an ion, or a molecule. And these unit cells are cubic, meaning they're 3-dimensional. This illustration is 2-dimensional, and so we have a square, but in actuality they're 3-dimensional, and so they're actually cubes. We're going to keep it simple and look at structures where all of the atoms are identical. So we're looking at basically elements as opposed to ionic compounds where you might have a sodium ion and a chloride ion, 2 different kinds of ions. So we're just assuming that all of our lattice points are the same kind of atom. We're going to use different colors. The different colors are just to help us see what is meant by the drawing. They do not represent different atoms or ions. So we refer to something called a coordination number. That's the number of atoms with which each atom is in direct contact. So how many atoms are touchingly close to this one atom? Those are the atoms that it can interact strongly with. The interactions with atoms that are not touchingly close are very weak, and so we're basically ignoring those. And when we refer to packing efficiency, we mean the percentage of the volume of the unit cell that's actually occupied by spheres, by the atoms themselves. So you can pack things, if you're thinking about packing to move to a different apartment or to a different house, and you think about packing things into a box, you can pack things very inefficiently where there's lots of empty space between the objects, or you can pack them in almost like a puzzle where they're very close together. So packing efficiency measures how much empty space there is in the solid. If we have a high coordination number, we will generally have a greater packing efficiency. The more atoms that are touching a given atom, the less empty space there will be, and so the greater the packing efficiency. These are some of the unit cells that we're going to look at. There's simple cubic, body-centered cubic, and face-centered cubic. And we're going to look at all of these in more detail. But this is a nice summary. It gives us the number of atoms per unit cell, an illustration of the structure. Here, the different color for this center atom is just to help us see it, because these 3-dimensional drawings are a little hard to figure out what we're looking at. This one is called body-centered cubic because there is an atom in the center of the unit cell. This is face-centered cubic because on each face of the cube there is an atom centered. Here's the coordination number for these different cubic cells. The edge length in terms of R being the radius of the atom, and the packing efficiency. We see 52, 68, 74. As the coordination number goes up, the packing efficiency goes up. So we're going to look at each of these in more detail. The simple cubic unit has the simple cubic unit cell has one atom at each corner. And so this picture differs from this one because here we're looking at whole atoms, and in this picture we're looking at just the unit cell. The unit cell is going to be only part of each of these atoms. But if we take this cell and reproduce it in all three dimensions, we'll end up with the crystal lattice. These atoms touch along the edge of the cell, and so the length of a side here, right down here, the length of the side of a unit cell is called L, and L is equal to 2 times the radius of the atoms. Because this is going from the center of one atom to the edge of it, that's R, the radius of the atom, and then from the edge to the center of the next atom. And so the length of the side of the cell is 2R. This one cell contains one atom because each of these corners is 1/8 of an atom. And so we've got 8/8, which is one atom. Any questions? Here we're trying to visualize how we figure out the coordination number. So right here, this is one of the unit cells with all of the atoms drawn out fully. And we're going to look at this one on the corner. And here's one unit cell, there's another, and one down here, and one back there, one here, and one here. And so we see that this atom is touching 1, 2, 3, 4, 5, 6 different atoms. So the coordination number is 6. It's touching 6 other atoms. So coordination number is 6. Again, the atoms per unit cell is 1. The packing efficiency of this structure is 52%. So just over half of the volume is occupied by atoms, and the other 48% is empty space. Any questions? A body-centered cubic unit cell has one atom in the center and one atom at each corner. So the atoms are touching on a diagonal, this diagonal from one corner diagonally across to the other corner. They do not touch along the edge. So we've got one in the middle, and these guys are on the corners. And because of this arrangement, they don't touch on the edges. So we can calculate the length of the side using geometry. This uses the Pythagorean theorem and all kinds of stuff that maybe you wanted to forget. The bottom line is the length of the side is 4 times the radius of the atom divided by the square root of 3. I don't expect you to memorize formulas like that. I don't think that's really worth the space in your head. Here is that body-centered cubic unit cell showing all of the corner atoms intact. Here it is showing just the parts of those that are in the unit cell. If we take this and we repeat it over and over again, we get the structure. That's what the unit cell is. To find the coordination number, we have to look at a bunch of different cells together. And here we're looking again at this one on the corner to see how many atoms are touching it directly. And so it's going to be 8. This ball, this atom on the corner, is only touching other middle atoms, the body-centered ones. It doesn't touch the atoms along the edge. There's a gap there. Because these purple ones and the gold ones, they're the same size atom. The packing efficiency for this one is 68%. Higher coordination number, higher packing efficiency. Then the face-centered has one atom at each corner and one atom in the center of each face. So the face of the cube, the square on each side, there's an atom centered in the middle of the face, and then there are atoms centered at each corner. So the atoms are touching along a diagonal face. The body-centered cubic, it touched from the corner of one cube diagonally across to the corner on the other side. But here, they touch diagonally along one face. And so finding the length of L is not quite as complicated, but it ends up being that L is equal to 2 times the square root of 2 times R. That's face-centered cubic. When we look at the coordination number, here's our atom in the middle. This atom is touching these other atoms, and it's really kind of hard to see in here, but the coordination number is 12. Packing efficiency, 74%. The face-centered cubic unit cell contains 4 atoms. I think I skipped that on the body-centered. The body-centered has 2 atoms, and the simple cubic has 1 in its unit cell. Yes, question? This one?
Yes. It says L equals 4R over square root of 2. How is that square root of 2 an X line?
The 4 is the square root of 2 squared. No, it's the square root of... I'll look into that. That does look funny, doesn't it? 4 is the square root of 2 to the 4th power. We'll look at that. That does look kind of strange, this guy right down here. Any other questions? So here's a problem that we could encounter in homework or on an exam. Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. So the radius is equal to 125 picometers. And we're looking at a body-centered cubic. And they want density. Remember that density equals mass divided by volume. So what we need to do to solve this problem is we need to figure out in the body-centered cubic unit cell how many atoms are in one unit. We can figure out the mass of that many atoms. And then we need the volume of that unit cell, excuse me. The volume of the unit cell is going to be L cubed, right? So volume equals L cubed. Length times width times height. On a cube, they're all the same. So that's the general strategy. So the mass, well, let's go back and look at body-centered cubic. So on a body-centered cubic cell, the length of the side is 4 times the radius of the atom divided by the square root of 3. 4r over the square root of 3. So L equals 4r over the square root of 3. And we know what r is. Let's think about units before we start calculating. We want grams per cubic centimeter. This is in picometers. So we can either convert this now to centimeters, or we can convert cubic picometers later to cubic centimeters. I would rather convert it now before we cube it. So I'm going to get rid of this guy because I like the space. So let's convert this to centimeters. So I got picometers on the bottom, meters on top, and then I want centimeters on top and meters on the bottom. It is possible to convert directly, but I don't think that's a wise thing to do. I wouldn't do it. I'm reconnecting. We're back. So pico, remember what pico means? Minus 12. The way I remember that is nano is 9. Nano's 10 to the minus 9. Pico is smaller, so it's 10 to the minus 12. And then centi is 10 to the minus 2. So when I do that, 125 I'm getting, darn. So one thing I don't like about this calculator, 1.25 times 10 to the minus 8. So R equals 1.25 times 10 to the minus 8th centimeters. So the volume is going to be the length of the side cubed. So volume is going to equal 4 times the radius over the square root of 3, and then we're going to cube that whole thing. So I'm coming up with 2.4056 times 10 to the minus 23rd. Anybody else get that? The unit's going to be cubic centimeters. Let me try that again. Uh, 1.25 EE minus 8 times 4 divided by the square root of 3, and cubing that. I get the same thing. Anybody else get that? Okay, thank you. So that's our volume. So that's one of the things we need to calculate the density. We also need the mass. So let's go back and look at the body-centered cubic. Body-centered cubic, we need to know how many atoms are in a unit cell. There's 2. That's something that you're going to have to either memorize or figure out. I won't give that to you. There's the one in the middle. It's body-centered. And then there's an atom centered on each of the corners. There's 8 corners, an eighth of each. So there's 2 in the whole thing. So we have 2 atoms in this volume. So we need the mass of 2 atoms of chromium. So 2 atoms, and there's 6.022 times 10 to the 23rd atoms per mole. And then we can look at the periodic table, and chromium is 51.996, 51.996 grams per mole. 2 divided by Avogadro's number times 51.996. And this is 1.72687 times 10 to the minus 22 grams. Now, let's pause a minute and think about significant figures. In my mass calculation, I used Avogadro's number with 4 sig figs and a mass with 5, and so that's going to limit my mass to 4 significant figures. 2 atoms is exact. In my volume calculation, the radius was given with 3 significant figures. Yes, that's a whole number, but that does not mean it's exact. So 3 sig figs here doing these calculations. 4 and the square root of 3 are exact, and so this will have 3 significant figures. Question? You got a different number for volume. Okay, let me check, because I do make mistakes. Oh, you got a different number for the volume?
Yes.
What did you get?
4.166.
4.166. I still get 2.4056. We'll have to figure that one out. Communicating with the calculator when we get to things like this can be a little bit tricky, and they all work a little differently. So I'm going to go up here and calculate my density. Density is the mass divided by the volume. The mass is 1.72687 times 10 to the minus 22 grams. Volume of 2.4056 times 10 to the minus 23rd cubic centimeters. I'm getting a density of, with 3 sig figs, 5.31 grams per cubic centimeter. Anybody else get that? Okay. Is that a reasonable density for a metal? Yes, it is. The density of water is 1 gram per cubic centimeter. The density of mercury is 13.6. Chromium at 5.31 seems pretty reasonable. Any questions? I'm going to check my answer here. I have a periodic table on my phone that has all kinds of cool information on it, including densities of elements. The density of chromium is 7.15, so that's not matching up super well. So I made a mistake somehow in my calculation there, and it should be 7.18, which is good news because looking up the actual density of chromium, which is 7.15, 7.18 is so much better. So I must have punched in a number wrong. Any questions? Questions like this with density are probably the most likely sort of questions with these different packing structure formulas. They do require a certain amount of problem solving and thinking. Okay, how can I figure this out based on these little bits of information? How can I put these things together to find the answer that I need? So what we just talked about is one way to look at packing structures of crystalline solids. Another way is to look at how the atoms go together in layers. So in the simple cubic structure, one layer of atoms is arranged in a square pattern, and it's lined up exactly on top of the atoms beneath. So think about putting round Christmas ornaments into a box without dividers, and packing them in. Or think of putting marbles in a box. So here, the balls are put in a square pattern, and the next layer sits exactly on top. So this one is centered on the one below, and this one is centered on the one below. And that gives us the simple cubic structure. And here, pulling this out, this is the simple cubic unit cell. There's a lot of empty space in this packing method. And if you've ever tried to put marbles or Christmas ornaments in a box, you know that they don't want to sit like this. They want to fall into the little divots between. That's what happens with this second approach. So here we have layer A, and then layer B is going to be offset, so that layer B is sitting on the little divot formed between the atoms in the lower one. So it's offset by a half of an atom in the x direction and a half an atom in the y direction. That's more efficient. This is called closest packed. There's actually more than one closest packed, but this is one of them. In hexagonal closest packed, there's actually 3 layers that are different. Hexagonal closest packed, we have layer A and layer B. I'm sorry. Hexagonal closest packed, there's just the 2 layers, layer A and B. So it goes A, B, A, and they repeat over and over again. So the first and the third layer are going to be directly on top of each other. The one in the middle is offset. This gives us a coordination number of 12, a packing efficiency of 74%. The unit cell here is hexagonal. It is not a cubic unit cell. It's a hexagonal unit cell. So when we look at this structure, the only way we can get a unit cell is by going with a hexagon. And so we've got, there's angles here of 120 degrees and of 60 degrees, etc. If you take this and repeat it over and over again, you'll get the hexagonal closest pack. Cubic closest pack has the 3 different layers, where the third layer is offset from the first. So layer A, layer B is sitting in the little divots formed by layer A. but then layer C is offset from the first layer. And so we get an ABC pattern. This also has a coordination number of 12 and a packing efficiency of 74%. This is identical to the face-centered cubic unit cell. So here's our 3 layers: a green, a red, a blue. Stick the green on top. So these layers are offset to each other. Put these together, tip it on its side, sort of at an angle, and then we can cut out a cubic unit cell from that, and that will give us the face-centered cubic. Is this all making your brain hurt yet? It's kind of hard to visualize all this three-dimensional stuff so early in the morning.